All right, so today we're doing a deep dive into a really fascinating, almost deceptively simple modification to large language models. We're talking about gated attention, specifically the work from the Quinn team.
That's right. And the key isn't just the gate itself, it's this tiny sigmoid function, but where they put it.
Exactly. It's all about the placement. Putting it right after the main attention calculation, a position they call G1, seems to be unlocking some massive results.
It really is.
So our mission today is to unpack why. Why is this one specific surgical placement at G1 the secret sauce that seems to fix these deep-rooted flaws in the transformer architecture?
I think foundational fix is the right way to put it. This isn't just, a minor tweak for a couple percentage points. We're seeing immediate, tangible improvements in training stability and really impressive long context performance.
Okay, so let's get into it. There are two big benefits this placement gives us, right?
All right, let's start with the first one. Expressiveness.
The model's ability to learn complex patterns.
Exactly. So the core architectural problem in a standard attention block is that you have two key layers, the value projection and the final output layer, and they're just two linear operations, one after the other.
Oh.
Mathematically, that setup can just collapse into one single, simpler linear mapping. It's like a low-rank shortcut that seriously limits what the model can actually learn.
So wait, why does putting the gate at G1 fix that specific problem? I mean, couldn't it go somewhere else?
That's the critical question. By placing that sigmoid gate right between those two linear layers, you're injecting a non-linearity.
Ah.
It breaks that mathematical shortcut. It forces the model to actually use the full depth of the transformation. So that's benefit one. No more lazy math, much more expressive power.
And the second benefit, which is where I think it gets really interesting, is that this same little gate also introduces incredible sparsity. Is that right?
Precisely. The sigmoid gate naturally produces these very sparse input-dependent scores, and what's really fascinating is that the best performing versions are head-specific.
Meaning each attention head gets its own unique filter.
Yes. And that's absolutely crucial for filtering out context that's irrelevant to the token being processed right now. It lets each head specialize.
That head-specific filtering sounds incredibly powerful. And that ability to just ignore irrelevant stuff seems like it would directly tackle a huge stability issue we've been hearing about, the attention sink.
It's a direct counter, yeah. The attention sink is this phenomenon where baseline models, especially with long context, just get fixated. They dump a huge amount of their attention on the first few tokens, basically ignoring new information.
And the numbers in the source material were pretty shocking. It was something like 46.7% of all attention scores across all layers were just pointing at the very first token.
Almost half. It's staggering. Think of the wasted computational capacity.
So what's the consequence of that? I mean, of half the model just staring at the beginning of the text?
The consequence is that the model can't adapt. But this strong, sparse gating at G1, it acts like a bouncer. It says, no, you can't just fixate on the start. It forces the attention to be distributed more meaningfully.
And it drives that number down.
It drives it way down, from 46.7% down to just 4.8%. And by eliminating that sink, you're also getting rid of these massive runaway numerical activations, which is probably the direct cause of the improved stability during training.
Okay, so let's connect that to the real world. What does this mean for researchers actually training these models?
It means more reliability. You see a near elimination of those really frustrating loss spikes that can derail a training run. And because it's more stable, you can be more aggressive, you can push the maximum learning rate higher.
Which means faster, more efficient training. That's a huge win for anyone trying to scale these things up.
And it doesn't stop there. That stability translates directly into better performance on long context tasks.
Right, the extrapolation.
Exactly. Because the model isn't relying on that attention sink crutch anymore to sort of manage its attention scores, these G1 models are just way better at generalizing when you stretch the context length using techniques like yarn.
So you push them to 64K or 128K tokens, they don't fall apart like the baselines do.
They significantly outperform them. It's a much more robust architecture for long sequences.
So to summarize the key takeaway for you listening, this isn't just some random architectural tweak. Placing this head-specific sigmoid gate at G1 is like a surgical intervention.
It is.
It simultaneously fixes the low-rank expressiveness problem. It introduces meaningful, input-dependent sparsity, and it almost completely eliminates that debilitating attention sink.
And that leaves us with a really interesting final thought. We now have the empirical data, we can see what happens, but the deeper theoretical link is still an open question.
What's the connection between getting rid of the attention sink and this newfound ability to generalize to crazy long sequences.
Exactly. Does getting rid of this one bad habit, this architectural crutch, make the entire model inherently more robust to future scaling challenges we haven't even thought of yet? That's the really exciting question to think about.